Hello, and thank you for the opportunity to present this paper. My name is Eduardo Romero. I am a PhD student at The Ohio State University, and I will present on memory mapping and parallelizing random forests for speed and cache efficiency. Let's begin by discussing what memory mapping is. So, it is a transformation of the decision tree into a table-like structure in which every entry can be looked up in constant time. So, for example, in this decision tree, every possible outcome of the decision tree can be mapped into, or every possible leaf of the tree can be mapped into one row of this table and therefore can be indexed in constant time given the input features. So in this example, an input that would normally follow the f sub a, f sub b path um, and would answer no based on this leaf node would be mapped into these two entries. And the reason this is two is because to be able to represent it on a table, it is necessary to encode every possible value that any of the features could take, and the the value of each column must be a match to perform a lookup. So in this case, every possible value of C must be taken into account to um, to have two. And of course, while this provides an advantage of constant time lookup, it also grows exponentially on the number of features, which makes it impossible to memory map in this naive, uh, simple way an entire random forest. To solve this problem, we have proposed the following structure in which we have three phases for the algorithm from a trained forest into a list of tables and dictionaries with a Bloom filter for inference. For time purposes, I will discuss in a lot more detail the phase one of the algorithm, while only briefly going over phases two and three. And for more details, I would refer to the paper. The compression algorithm starts by looking at all of the possible paths of each one of the trees that correspond to the forest. So in this case, we can see this small table here corresponds to tree 1, and this small table here corresponds to tree 2. And then second step after listing all of the possible paths is to sort each one of the paths internally. So H0, A0 would actually become A0, H0, changing the order of these features. And this helps both group similar paths that have very similar structures and very similar features, just in a different order, as well as it helps when the input features arrive, identify quicker which feature belongs um, to a position. And then after this, paths are sorted uh, together to allow for similar paths that belong to different trees to be grouped together and be calculated together. So in this case, we can see that the path that has feature A as, with a value of 0 actually gets mapped with a subtree that corresponds to that. This clustering leads to smaller memory map tables in which in each one of them there's a full memory mapping of every possible value of all the features that correspond to all of the paths that are mapped there. In this case, we only need a memory mapping of B and H because A sub 0 is common in every path that corresponds to this. So in fact, A sub 0 is used as the key of that dictionary rather than needing a memory mapping, and it is extracted in this way, making the table smaller. So the small drawback is that not every result can be computed immediately, and possibly more than one dictionary entry must be accessed because in this case, for example, all the entries where H is 1 correspond to a subtree that is mapped elsewhere. So results should be looked up independently. However, this permits a much smaller table. All of these three tables combined have 10 entries, while the naive memory mapping would have 16. And this dictionary um, maps the input features to each one of the corresponding tables. Before going into more detail for why paths are uh, clustered together in this way and what are the advantages of this approach, uh, let's discuss for a moment how they are divided. And in this case, there is a tunable parameter that was hinted at in the previous slide, which indicates how many features that are not common to every path can be added into a cluster. So for example, in here, after adding A0 and B0, both of them, both A0 and B0, are common to every path at the beginning because there's only one path there. After A0 and B1 gets added, then B no longer is common, so only A is, and at this stage, B is just uh, one feature. All of these two can be considered together because um, every possible value of B will be considered in the table as we saw before. The next path can also be added with A0 and H0, in which case now we have two of them. Because of this, we cannot add A1 and C0 because this would actually add two more um, uncommon features. Therefore, by setting this limit, we can control how much each table grows and how many dictionary entries we have. This tunable cluster size impacts directly the efficiency of the algorithm because by increasing the number of dictionary entries, we increase also the number of elements that must be computed sequentially during inference. While on the other hand, increasing the table size, this can incur into memory inefficiencies, can make the tables too big, not fit in cache, and therefore have cache misses and consequently slow down the algorithm as well. So finding the right value for this parameter is essential for the algorithm, as well as the dictionaries and the table entries can be split into multiple cores and they can be split separately or together. More details on this on the paper, but there's the second phase of the algorithm searches the space for the ideal set of parameters for this. Before discussing phase 3 of the algorithm, it is necessary to understand how inference is made. So during inference, once a sample comes, each individual entry of the dictionary is evaluated. So first it is in this highlighted example, it is checked whether H has a value of 1, E has a value of 1, and then if both of those are true, then just in that case, the value of D gets evaluated. And then the values of these three features plus the dictionary ID are hashed into a function that should map to the table entry um, that corresponds to it. And this is done in this way because in the case where only one core is used, recombining the tables can be more efficient because it avoids branch mispredictions by looking into different tables and loading different tables depending on the input. One table that has all of the entries performs better. Phase 3 of the algorithm deals with the possibility that multiple dictionary entries lead to a lookup as described in the previous slide, while only one of them is correct. And this can happen when one of a set of features that are common in every path is a subset of another. And in that case, it is necessary to just also have the dictionary ID in the table, in the final lookup table. So once a lookup is performed, the the algorithm can check whether the dictionary ID that was used for that hashing matches the dictionary ID that was found in the looked up entry, and therefore can verify whether their lookup was a false positive or not. To evaluate our algorithm, we use the MNIST dataset for a few random forests, and we compare to state-of-the-art forest packing, and we compare using different number of cores as well as um, different settings for the maximum depth of each tree that was allowed. And our approach performs orders of magnitude better. Here, black and yellow correspond to a forest with maximum height of 6, um, and green and gray correspond to a forest with maximum height of 10. So in all of these settings, our approach performed much better than state-of-the-art approaches. In the future, we expect to improve on this algorithm by providing a better way of searching the space of possible values in phase 2. Right now, it is done by testing all of the possible different values or testing a subset of values. Um, we want to explore the results on different data sets as well as explore some interpretability benchmarks, because interpretability is one key advantage of tree-based algorithms over neural networks. Finally, I want to refer to the paper for packing that we use for comparison, and I want to thank you for your attention.